present mini project about food services and drinking places. There are 4 main tests. Test 1 is exploring the collecting data YT. First, we clean and repair the dependent variable YT, which was collected from F4ED with monthly frequency and non-seasonally adjusted unit. To ensure consistency across all variables, we align the timestamp and keep only the overlapping period. After pre-processing, our final dataset includes 405 valid observations. From the descriptive statistics, we can see that the data show an increasing pattern over time. The distribution is rescue indicated by the median being lower than the mean. The standard deviation is about 22 and 120, which is approximately 52% of the mean, showing substantial variability. Additionally, the interquartile range is around 35,000, meaning that the central 50% of observations are widely dispersed. To test for normality, we use the Anderson-Darling test. The results show an AD status of 12,398 and a p-value below 0.005. Since the p-value is smaller than the 0.05 significance level, we reject the known hypothesis. This means that YT does not follow a normal distribution, which is also clear from the probability plots, where the points deviate significantly from the reference line. We then fitted the data to several common distributions. The normal and Weibull distribution show poor fit with high AD statistics. The log normal distribution fits moderately well. However, the 3-parameter Weibull distribution performed best with the lowest AD statistic of 0.782, indicating the closest agreement between the model and the data. Finally, based on the goodness of fit table and the probability plots, the 3-parameter Weibull distribution is the most appropriate model for describing YT. It captures the right scale nature and variability of the dataset better than the other tested distributions. Therefore, we select the 3-parameter Weibull distribution as the best fit for test 1.
Test 2 is characterization of time series YT. So first is the time series plot. So by looking at the time series plot, you can see it's suggesting an exponential and directed growth pattern, and it's indicated multiplicative seasonality. It also has a non-constant variant that grows over time. So in the instability in the data, you can see in the index 330, 340, it has a sharp drop followed by the immediate recovery. It's likely caused by the system error, stock out data recording issues, or external description. So here is the autocorrelate function for YT. So you can see the successive observation are highly correlate, and the ACF value remains significant for many lag and decline slowly. And the last one, autocorrelation, is very close to 1, indicate very strong persistence. So it suggests that the series had a clear upward trend and non-stationary data. So by the analyze the characteristic of the data, our group proposed 3 methods to conduct the predictive calculation. The first one is Winter method with multiplicative model. So it's designed to handle both the upward trend and expanding seasonal variant of our data. The next one is decomposition with multiplicative model. So this method helps us separate the 3 components: trend, seasonality, and noise. The last one is the Holt linear exponential smoothing. So it used exponentially weighted moving average best value to capture involving local linear trend in the data. So it provides high flexibility in the trace rate to track both level and trend independently. So we use Minitab to calculate 3 method, and here is our result. So you can see based on this result, the best method is Winter method, and the second place is the Holt linear exponential smoothing. So here is the future value forecast for the Winter method. You can see for the next tail period, it predicts a stable year with the robust upward trend, and it has the record peak period 416, and it has a consistent seasonality and notable dip in period 409 to 410. Here is the forecast by the Holt linear exponential smoothing. So the demand rose steadily, and it's predict continuous positive growth with no downturn. However, the forecast is entirely smooth, falling to capture specific seasonal fluctuation of the data. So here is the forecast value for 3 periods by our past technique is the Winter method. You can see it's possible to check the confidence interval. These predict value forward in. You can see the lower and the upper in our forecast value result. So it means that it's there 95% probability that our prediction will lie in that range from the lower to the upper.
Okay, next is task 3 forecasting using a multiple linear regression model with the observation variable YT explained by 5 independent variables x1t to x5t. In addition, our group used Minitab to generate random data following a uniform distribution U010 and obtain the following results. This is the value x6t, which is stored and use an independent variable in the regression model. Next, we use the record data function to categorize the CPI variable into good, warning, and bad. The result are as follows. After obtaining the data, we use Minitab to perform the regression analysis. Next, the F value of 2575.88 with a p-value of 0 indicate that the overall model is statistically significant. The t-test show the variable x1, x2, x4, x5 have p-value smaller than 0.05, meaning that they are significant impact on YT. R square equal 97% and H R square equal 96.96%, so that the model has a very high explanatory power for the dependent variable. the X1 VIF equals 60.93 and X5 VIF equals 37.22, revealing that several multicollinearity exists in model. Next is the normal probability plot. The data point do not lie on one line, especially at the extreme on the tail, indicate that the residuals are not ideally normally distributed. Residual visit fits under the data point appear centered around the zero line. There is an increase in variance and the fitted value increase. This suggests heteroscedasticity. Residual visit order. The data point that are randomly scattered around the zero line and no systematic pattern is clearly visible based on the observation order. This suggests no clear evidence of autocorrelation in the residuals relative to the data collection. Finally, is the solution. The solution for the model refinement. To address multicollinearity and assumption violation, we propose variable refinement and advanced modeling techniques. Variable refinement eliminates insignificant variable like x3 and x1 due to its high VIF, and rerun the model with x2, x4, x5, and a categorical CPI. Last one is the handle autocorrelation. Utilize an ARIMA model to capture the autocorrelation structure in residuals. Consider logarithmization or differencing for variance stabilization.
Okay, so let's move into the last on the list. Moving to task 4, we applied the Pottinskin approach to the forecast, the sell-food service, and ranking places. So the first one, let's look at time series plot of our original data we analyzed in task 2. So we will pass this one, and you can see the data show two clear characteristics. So in the autocorrelation function for YT, the large one is extremely high, it's 0.979, with a value slow to 1. This means that this month data is almost entirely dependent on the previous month. The slow slide from large 1 to large 65 show high and statistically significant correlations. So to the constant variant, the fluctuation gets larger as time goes on, and which is called the megaphone effect. So this is the sharp. Because the data has non-constant variance, the strong strain, so it's non-stationary, we cannot run ARIMA on it yet. So we check the podcast, the optimal lambda was minus 0.04. Very close to 0, so we apply the natural log transformation to just stabilize the variant. And even after log transformation, the strain remains, so we apply the first order differencing d equal 1. And look at the figure, this one, the strain is removed and the theta oscillates around 0. Thanks to log and thanks to differences. Only when to the data stationary can ARIMA model predict correctly. However, the ACF plot still show the strong spike at the last 12, 40, 24, 6, 36, 48, 16 indicates strong seasonality as well. The partial autocorrelation function for this one still display the prominent spike at last 12. The series still exhibits strong seasonal pattern. It's not yet stationary. This makes it difficult to build accurate ARIMA model without further seasonal differencing or adjustment. So we still do the identified ARIMA model to pass this YYT, estimate the model parameter and perform this one. So we use the Minitab to find the best ARIMA model, and we compare three candidates model. And we choose the 514, ARIMA 413, and ARIMA 211. So the first one, ARIMA 514, this model failed. It was over parameterized, meaning it was too complex, and some coefficients were not statistically significant. The p-values is larger, 0.05, indicating it is not significant. As well, the Armstrong-Cox test at the seasonal peak is give the p-value 0.0, meaning the residual are not rhinos. The strong residual autocorrelation, especially the seasonal large, show the model is inaccurate and cannot capture underlying structure. And we're moving to the ARIMA 413 is what to our pet choice because it has the lowest AIC, and as well all the parameter AO and MA was statistically significant with the p-values close to 0. But however, the Armstrong box still have the p-value 0.0. It is a seasonal large, meaning the residual are not random. And the last one we still have the compare with 211, and as you can see, it is there with ARIMA 431. So 413. So as you can see, the ARIMA 413 provide the test balance with the lowest AIC, and all coefficient significant p-values is smaller 0.05. However, the model still failed the Armstrong-Cox test at the seasonal large, residual are not random. So I suggest that the pool ARIMA cannot capture the strong seasonality at the food service and ranking places data. So the ARIMA is required or accurate modeling. So through that, we generate the forecast for the next 5 period in order to.
So we compare with the window method forecast that we calculate in task 2. So you can see by the ARIMA, it saw the pattern smooth lining upward trend, and the prediction saw the steady growth range from 99,000 to 100,000. It had the limitation that it acts as a baseline average, failing to capture monthly peak and growth. For the window method forecast, it saw the pattern, one dynamic cyclic pattern fitting the historical seasonality, and its prediction showed a strong seasonality with deep growth and record peak, and it can accurately reflect the volatile nature of demand. So ARIMA risk can underestimate peak demand by 10,000 units, like stock risk, And the winter method is superior for operational planning like inventory or staffing. So here is the end of our presentation. Thank you for listening.